A charge-coupled device, a CCD, is a highly sensitive light detector originally developed in astronomy for digital imaging. These devices doubled the ability of telescopes to detect light and allowed astronomers to finally obtain color images of very, very faint stars. They're now, however, found everywhere, from digital cameras, webcams, digital video recorders, scanners, photocopiers, you name it, they're all over the place. As you can see here, there is a small silicon chip with a surface covered in a large number of very light-sensitive elements called pixels, or picture elements. In this diagram, you can see them more clearly, with single pixels outlined. These pixels are defined by insulating channels along the side, or one side of the surface, and conducting panels along the other. So they're insulated from each other on the one hand, but there's also these charge conductors along the other. In order to understand how these pixels work, it's worth going back to the photoelectric effect, which is vital in understanding what happens. Electric effect. You should remember, with all the revision that you're doing, that when a photon, a particle of light, hits a surface of certain materials, if the photon is above a certain threshold level, okay, which is equal to the work function, what should happen is an electron takes the energy from that photon, uses some of the energy to escape, and then is released. So this is pretty much how the pixels react to light and convert it to electricity. As you can see from this picture, this is the incident visible photon hitting the pixel, which is made of a semiconducting silicon, and therefore, accordingly, there's a release of electrons. Now, if you can imagine, this is all initiated by you pressing the button to switch, to take a photo, okay? So the shutter on your camera opens. The shutter opens and incident visible light comes in. Now, the intensity of the light is proportional to the number of photons. So, more intense light means more photons. And because there's more photons, there's more electrons. By electrons, we can also talk about charge. Because what in fact what we're doing is we're causing an electron charge to collect in this little pixel well. And it's very, very much like a capacitor. A capacitor holds charge for a certain amount of time until it's needed. And a pixel does exactly the same thing. If we think about the capacitance formula, potential difference equals charge over capacitance, we can see that the potential difference is proportional to the charge. So what does this mean? That when you take your picture, the shutter opens, intense light comes in, the more intense the light that comes in, the more electrons that are given off. The more electrons that are given off, the more potential difference that's generated across the pixel. So what you have there is a register of brightness, but as small potentials. Now, when does this process stop? When the shutter closes, when you finish taking your photo. So the shutter closes, and what you've got is an array of lots and lots and lots and lots and lots of pixels, each with a little well of electrons, and each of these little well of electrons has an associated voltage which correlates to the brightness. In fact, what we have here is a very, very clear analog to digital converter, because you've taken digital conversion, because you've taken light waves, which are analog, and you've stored them as digital information, which is numericals, basically voltage, high voltage, low voltage, high voltage, low voltage. So a CCD is a perfect example of an analog to digital conversion method. Brightness can now be correlated to numbers. A very bright one could be correlated to a 9, a 7, a 0 if it's a dark square, and you can build a map of what the picture looks like by having a numerical value associated with the level of brightness that used to hit the pixel. So let's just say if you had very, very, very intense light here, it correlates to a 9. Now, how would that be stored? Of course, you wouldn't store it as a 9, you would store it in its digital format. Okay, so you'd represent it as a byte or a 0101 or its equivalent. Okay, so this is a perfect example of how a wave formation can be converted into a digital message. So how do we retrieve the information from a CCD? Well, as you can see from this diagram, the information from each pixel is then shoved down the array. The charge is shifted down and then collected in a serial register at the bottom. This diagram represents a nice analogy. Raindrops represent the photons of light collecting in these buckets. There they are. And the serial bucket array, which is on a turntable, collects arrays as it moves down. So you'd have a parallel register shift. The first row is collected. So this is moving along. The first is collected. And then if you have a look at the third picture, it's read out. And collected at the end. In reality, this calibrated measuring container would represent the amplifier and an analog to digital converter, which is what finally produces the binary signal.